Hi, I'm Charles, and welcome to part 19 of the OpenSCAD video series. In this part, we're going to be talking about a technique called a chained hull or a serial hull. They mean the same thing. Before we get started, I need to give credit where credit is due. So we're going to go over to the internet, and I'm going to talk a little bit. So I first learned about this technique in a blog post, this blog post. At this address, it will be in the description. The link will be in the description, and it is by Jeremy Francois. His name's here at the bottom. So it's just the chained hull and serial hull, chained hull. It means the same thing, but they're described in this blog post, and I have a slightly different take where Jeremy uses modules, and I don't. But other than that, it's essentially the same technique, so I owe credit here, because this is the first place that I learned about it. So, without further ado, let's get into it. So, we learned before what the hull operator does. If we have two objects, so that's a first object. Let's see. So we have two objects, and we want to fill in the space between them, because that's essentially what's going on. We use the hull operator. And that fills in the space between the objects. Now this has another very useful use. What we're going to do with this operator is essentially create a path. Or if you define a path, then we're going to essentially fill in that path with whatever object we choose. So, your first idea, okay, let me just give an example. I'm going to use a for loop to generate the path. So this gives us a quadratic function. Now we have to divide it or else it's way too far. There we go. So this is, this looks filled in, but as you can see, it's very choppy. And to illustrate my point, I'm going to take maybe every 5. Maybe even more, every 20. Okay. So this is going to be a good example for us. So we have our shape, and this is just a 2D example for now, but we're going to get into a 3D example. A very complicated 3D example, so I'm excited for this. But essentially, we have our quadratic function, x squared over 100, and we take every 20th value. And so what your first idea might be to do is hull the whole thing. Maybe that'll give you what you want, but it will not. It just joins all the space together, and then that's a pain in the butt. So what we have to do, we do have to use the hull operator, but not like that. So essentially what we do here is what we're going to do. Maybe we're going to create 2 of each object, or almost every object. We only need one of the first and one of the final, but everything else needs to have 2 copies. So to do that, we copy and paste inside the for loop. So now we have two copies of each object. And to prove this, I can move this up 30. So now we have two copies. But what we want to do, we don't we don't want them to be exactly over the object. We want them to be the next one. So this object here, we want this one over here. And this object here, we want over here. And this object here, we want over here, and so on and so forth. We want it to be the next one, so that essentially what we can do is we can hull these two objects, and then we can hull these two objects. So what we need to do here, we have to say, so we have our first object here, that corresponds to this one, and then how do we get this one? So we know we're, in this case, we're stepping by 20, so we know that this is the function at 20, or when we've moved 20, when I is whatever this value is plus 20. So what we do, we say I2 is equal to I plus 20. And then what we can do is everywhere where I appears in this first part, let me comment this. So we say first object, and this is the second object. So I2 is equal to I plus 20. And so we just replace wherever I appears, we replace it with I2. So let's preview that. So now what we see here is kind of what we want. We now have, they've moved over one, but now we have this extra one. So what we can do to get rid of that extra one is just subtract 20. So now they're all misaligned by 1. So what we can do here, when we do this, basically the only step left to do is to hull the objects. So now we have our two objects. We have our first object, which is here. We have our second object, which is here. And now we have to hull them. And we'll get a quick look what that looks like in 3 dimensions with them up here, so we kind of get an idea. And then I'm just going to move it back down so we get a very clear picture of what we want and what's going on. So as you can see, they're all hulled to the next one. And now I'll take this back down to 0. And we get our line. So if we wanted it to be smoother, because as you can see, it's a little choppy right now. We could use a finer step. Let's use 10. But then everywhere where, actually the step is here, but everywhere where the step is used, we have to change it. So the step is used here, and the step is used here. So now we can see it's a bit finer. And we could take that all the way down to 1. Might be a little bit hard to render, but I can do that. Let me do that. So let me keep the view on it so you can see how it changes. And that's much finer. And this is renderable, and you can use this. And so this creates essentially whatever path you were trying to make in the first place. So now I'm going to take this back up to 20 just for just keep it what it was before. So a little bit not as fine, but I'm just going to copy and paste this and make a generalizable sort of thing, a more parametric idea. So I'm just going to get rid of this for now. So what we do is we can define a step. I'm going to say step A because this is, I'm going to do another example where I want to use step. So this is step A is equal to 20. And then wherever we use the step, we just put step A. And we get the exact same object, except now, when we change this value, we get something finer and finer. And dare I go to 0.5? Hopefully I don't crash the program. Let me save just in case. And nope, we're good. And so now it's incredibly fine. But you might notice that you get sort of a wonky shape here. It's not quite the line because maybe a square isn't the best thing to use. A circle or a cylinder might be better, or a sphere, depending on what you're going for. Because as the angle that connects the two cubes changes, I want to say diameter, but it's not diameter. The width of the line changes because the diagonal of a square is greater than the length of its sides. I know you could use other shapes to do this. And another thing that's great about this is you can, because this is in a for loop, you can change other parameters of the shapes. But it's important to remember that if you change parameters of the first shape, you have to change the parameters of the second shape. So let's say we want to say 5 times sine of 2 times I. And if we do this, we get an interesting shape, although it's funky because we haven't changed the parameters of the second shape. I'm actually going to increase this, maybe increase this to 2, just so it's a little bit easier to render. So you can see that we get these jagged things because we haven't changed it in the second object. So we're going to change this in the second object. And remember, we have to have I2, so we change it to I2, and we get this interesting shape. So, yeah, that's kind of, those are the basics, but I'm going to go into a more complicated example now. So essentially what we're going to do in the next example is trace the exterior of a torus. Now, a torus, I can just show so let's say we translate this 50. Okay, so if we have a torus, I mean, this isn't a torus. I'm going to show that in a second. The linear extrude command. No, not linear. Rotate extrude. So if we have, we're going to make a torus, and there are a few values that are important. So we have our circle over here, which will be the size of the ring of the torus, and that will have a radius. So it's important to note that radius, the radius of your smaller circle. And then we have the radius to the center of our smaller circle. And that's important as well. So in this case, we know the radius of our small circle is 10. The radius is 10. And the radius, because we've translated by 50, the radius from the origin to the center of our circle is 50. So we'll rotate extrude. And this is a torus. This is essentially a torus. So what we're going to do now, we're going to trace the outside in a circular rotation fashion. Hopefully I don't lose anybody. This is a bit of an advanced example, but I want to show it, so hopefully it goes well. So first what we're going to do is create our cylinder. And to start, we're probably, we'll have a radius of 1. The center will be true. We're going to keep the FN value fairly small. Let's say 25, just because if we make it really large, then it's going to be difficult to render. And maybe you can increase the size and render at a larger one, or preview at a larger, a more detailed shape. You can preview a more detailed shape, but for this I just want to keep it simple, just to demonstrate the process. So the height, now here's the thing, a lot of the time with a chained hull, you want to use very thin slices. So we're going to take the height of this object at 0.001. So this is 1/1000th of a millimeter. So this is an incredibly small piece, almost so small that I don't even know if 3D printing can be that accurate, maybe in some cases, but it's generally, in this case, it's not noticeable. It's so small. So let's take a look at our cylinder. So here we go. We have this flat disc, just a little jagged. It's okay. It's a good approximation. So we need, what we're going to do with this, so first we're going to rotate this 90 degrees about the x-axis, just so it's flipped like this. So now we need a we will say T radius for the radius that we had from the center to the center of our circle, and we're going to make that 50. And we will have our circle radius. So circle rad is equal to 10. And that is the radius of our circle, our little circle that we're going to make. So essentially what we're going to start wanting to do, we want to translate our circle out by our small circle radius. It appears I might not have been clear in exactly what's going on, but if you follow along, you'll understand. Hopefully you don't have to watch this too much more than 2 times, but that might be necessary just to understand where we're going with this and the example that I'm showing. So we want to translate this by the C radius in the X direction. And we're going to want to set up a for loop. And I think I've used I. Yes, I've used I. So we don't want to use I. We will use Q. We'll say 0 through maybe 1. And we're going to use step we'll say step equals 0.01. Actually, you know, it might be better if it's smaller, so 0.001. And we need to put step in there, of course, and add the semicolon so our code compiles. So that's okay. So what we're gonna do is we're gonna rotate this around the y-axis. And there's a certain number of rotations that we're gonna want. So we'll say rotations. Let's say 5 for now. So we'll say, because if we look at it, the y-axis in the positive direction, we know that a positive angle will go this way, and I want it to turn this way. So I'm going to make it negative rotations times 360. So this will, if it's 2, it'll be 720. If it's 3, it'll be 1080. So it will rotate this full amount. And essentially what our for loop is going to do is it's going to bring us from 0, where it's not rotated at all the values, or a bunch of values, to the top one, to when it finally ends up as 1, and then it has a full rotation. So we multiply by Q. And that gives us our ring. So a good first method, if you're trying to create a chained hull, is just to create your first object. Even if it's thin or it's simple, that's fine. You just start with that, and then you add in the second object later. You can just copy and paste and just change a few variables, and that's really easy. So the best way is just to start with the first object and don't worry about the second object, or you'll have to keep going back and forth to change values. So we have our ring. It's still probably not pretty clear what I'm trying to do, but it should become pretty clear in a moment. So we want to translate this out. So this is kind of the ring for our torus. We know this is the radius of our circle, which should be 10 from here to the center of actually our little circle. But don't worry about that. We have a little circle. And now we want to move this out to the radius, our torus radius, which is 50. So no, that's not. There we go. Okay. TRAD. Okay. So now that's moved out. And now we want to rotate this again. And for each value, we want to rotate this around our z-axis. If you really wanted to, if you knew specifically what you wanted, it might be easier to make a module for this. But I like using just the code because it allows you to easily edit what you're trying to do. Whereas opposed to a module, it could be a little bit more complicated to edit what you want to do. So we want to rotate around the z-axis. So look at it from the positive, and we see we want to go in the positive direction. So what we're going to do is we want 360. We only want it to go around once because we want it to come back and be where it is, so we don't need to multiply by the rotations. So 360 times Q, because Q will go from 0 to 1, and by at 0 it'll be here, and at 1 it should come around and be back where it is, and it'll be a bunch of values in between. So let's see what that looks like. And there we go. That's essentially what I was going for. Maybe this is not quite as clear. Let me increase the rotations so we can kind of see the torus that it's outlining. 10. So you can see now that there's like a torus, and if I uncomment this, if you see what we're getting here, we have this torus, and then we have essentially rings wrapping around it. And what actually rotations does is it controls how many times it's rotated around. So if we just did 2, you can see there's 1 rotation, and it comes out, and then another rotation. So I think 10's probably good. It demonstrates it quite clearly. So now we have now we kind of have an interesting shape that we're going for. And this was not what we didn't want the torus. So now we have just this. And now what we can do, since we already have our shape, all we have to do is copy and paste it, and then hull them. And of course, change the second Q value. So it's important that we say Q2 is equal to Q plus step. And our step is 0.001. So just warning, this might take a minute to preview, just because it should be fairly computationally intense, because there's a lot of objects here. And the reason we're getting these shapes is because our cylinders are super thin, so you can kind of see that, I don't know, when you turn curtains or blinds, they kind of disappear. That's what's happening here. That's why it looks like that. But when we hull them, it shouldn't. So let me just make sure this is correct. It looks like it is. And now we'll hull the shapes. And just as one more reminder, we do Q2 is equal to Q plus step, so that we get the next object in our sequence. So we have a disk here and a disk here. And if we didn't add the step, or we added another value, maybe 1, we wouldn't get this one. So if we didn't add anything, we'd just have 2 circles or cylinders in the same place. If we added 1 or a different value, it might end up somewhere else. But when we add step, we always get the next one. So that's why we do Q2 is equal to Q plus step. So now let's reset the view and let's hull them. So yeah, it's going to take just a moment to load because it is really intense. And I could increase the speed by lowering the fineness, and that's why I left the FN value so low for the circles, because it is really intense. And there we go. There you have it. So that's a really interesting shape, and there's a lot that you can do with this technique. You can actually make a torus where the radius of this part of the circle, what did we call it? Our C radius, the circle radius, was smaller or larger. I mean, it changes. You can make it so it changes, but you can't do that with a rotate extrude, but you can do that with a chained hull. So this is one of the most powerful techniques in OpenSCAD, I would say. It's very, very useful if you're trying to make shapes, if you're trying to have a little bit more freedom with the shapes that you create. And as we can see, that's correct. It joins up at the end. That's good. So yeah, that is the chained hull module. Or not module. That is the chained hull technique. And as I said, it's one of my favorite techniques. It's very useful. One thing you might notice This doesn't happen in all applications of the chained hull, but let me move out to the side. But as you can see, we don't quite have a circle. Now you could use a sphere. So I will demo that right now, but I have to make this a little bit less. I will space it out a bit more, just because spheres take a lot more time to process. So if we do a sphere of radius 1 and the FN value of 25, this will kind of solve our problem. And if you have a lot of RAM and a lot of compute power, then you should be okay. This might be a bit complicated, but there are other ways around it. So another way around having to use a sphere to get a circle, if you're going for a circle wherever you are in going around, another method for that is to, if you take a cylinder, the cylinder that you began with, and you have the flat face of it point in the next direction that you're going to. So that is more of a sweep along a path, and that gets into more complicated math that I'm not going to talk about in this video. But yeah, that is how you do a chained hull. And there you go, that's it. Wait, it was more interesting before. 0.01. There we go. Awesome and smooth. Cool. So hopefully, I really hope you learned something in this one. This is one of my favorite techniques. Yeah, thank you very much for watching, and hopefully I'll see you in the next one.